Alright, so part 2, thermodynamics, the smackdown. If you look right here, the other way we calculate delta H besides Hess's law is we do it by bonds broken minus bonds formed. That's the other way. Probably the one you won't remember the easiest. So bonds formed. So when we go to do this, what we do is we have a table, a set of values for each of the different bonds. So if you notice, there's bond energy listed here, bond energy listed here. So when you go to find delta H, what you do is first have to draw the Lewis structure. So if you look N2, it's hard to read, but N2 looks like that. H2 looks like that. Actually, I forgot the dots there, kind of like you guys did on your N2s. I have an H2 here. And finally, I have a molecule that looks like this. N2H4 looks like this with a couple of lone pairs of electrons right there. So the first thing you have to do is you have to draw the Lewis structures to figure out what bonds are present. So if you notice, I drew that based on this using the Lewis structure technique that we learned. Then you have to go back and you do this. First draw the Lewis structure, get bond energies from the table, and basically what you do is you take the bond energy value, whatever it is, for that each particular bond, times the Stoichio coefficient from the equation, and the number of bonds in one molecule. If you happen to have two molecules, like I drew the H2 molecules on the previous slide, you're really only basing it on one Lewis structure, so you got to be careful. So if I look right here, first of all, N2, triple bond. Bond energy is 946. So I go over here. The value is 946. If I look at the equation, what's the coefficient? Stoichio coefficient is 1. Then I look at the structure I drew, and how many triple bonds are there? Well, there's only one. So 1 times 946 gives me a value of 946 right there. The next thing I'm going to look at is my other reactant is H2. There's its Lewis structure. The value for that's listed right there is 436. So I go 436. Next thing is stoichiometric coefficient. Coefficient's 2, so 436 times 2. And then how many bonds are in one of the structures that I drew? So I basically look right there. There's 1. So 436 times 2 times 1, I get whatever that value comes out to be. I pop that up there, and I have those are my bonds broken. Do the same thing on the other side. I first look up nitrogen, a single bond. When you go over here, nitrogen, single bond is 163. So I put 163 for this. The coefficient for the molecule is 1. So I'm going to put 1 right there, and then there's only one bond in the structure, so that's the bond energy there. The only other bond I have in this molecule is an N to H bond, and if I look, it's negative 389. Oops, that's negative 163. Whoops. So then I go negative 389. Coefficient of the equation, stoichiometric coefficient is 1. How many bonds do I actually see in the molecule? I see 4. So then I would basically take 389 times 1 times 4, get that value. 163 times 1 times 1, get that value, and that's going to be my bonds formed. Just by subtracting those two numbers, I get the value for delta H. Not too bad. Draw the correct Lewis structures. Remember stoichiometric coefficient, value from the table, and number of bonds in one molecule. All right. Next thing, we just did that. Gibbs free energy value. Going home to supper tells us that's the key part, the top of the mountain in thermodynamics. Whoops, maybe I can write it properly. Going home to supper. Ignore that right there. That is the Gibbs free energy calculation by knowing the sign for delta G. If delta G is negative, we say a reaction is spontaneous. If delta G is positive, we say it's non-spontaneous, and if it's 0, we say it's not at equilibrium. Key thing you have to remember, there's two ways to find delta G that they ask on the AP exam. The first thing is by inspection, by looking at equations and interpreting them. That's what we're going to do. The other way is actually by calculating it using going home to supper. Things you have to remember, when are reactions always spontaneous? If delta S is positive, delta H is negative, it's always spontaneous. And you have this in your notes. You have to go back and look at it. If delta H is positive and delta S is negative, it is never spontaneous. So it's the opposite of always. So when you have these two, if you know one, you kind of know the other. Then the only other situation is when both the signs are the same. For example, if delta S is negative by inspection and delta H is negative, we say it's spontaneous at low temperatures. If delta S is positive and delta H is positive, again you see the case where there's both the same signs, then we say it's high temperatures. Remember, if it's real plusy on a thermometer, if you have a lot of pluses, high temperature, hot, however you want to remember it, it's an easy way to remember it by inspection. Let's take a look. If you look right here, first thing I see is I see a value for delta H that is negative. So I just looked at my delta H value, it's negative. I have to figure out my delta S value by inspection. If I look, I have a gas, gas, gas. I use the mole rule that we learned in the previous video. I have 3 moles on this side, 1 mole on that side. My delta S value is going to be negative. When the signs are the same, negative, negative means low temperatures. So I would say at low temperatures that would be spontaneous. Next one, my delta H value is positive. So for the second one, B, I say a positive delta H. By inspection, gas, gas, gas. So I have 1 mole on the left, 2 moles on the right. Therefore, my delta S value is positive. Again, signs are the same. I go back and I look at the chart. If I have a positive and a positive, I would say that would be spontaneous at high temperatures. And that's how you do it by inspection. You have to read the problem. If it says it is a spontaneous reaction, it means delta G has to be negative. So if you look, this one you have to classify when this is spontaneous. So if you look right here, delta H is negative. Gas, gas, gas. I have 1 and 2. My delta S value is going to be negative. Therefore, it would be spontaneous at low temperatures. Next one, if I look right here, positive for delta H, already there. All gases, I go 2 to 4 moles on that side. My delta S value is going to be positive. Therefore, it would be spontaneous at high temperatures. Last one, delta H is negative. Delta S, 2 moles on this side, 3 moles of gases on that side. Delta S is positive, and that's the situation. This thing is always spontaneous. And that's how you predict, based on a chemical reaction. Look at the chemical reaction, figure out delta S based on the SLG rule, or base it on, actually base it on the SLG rule and find delta H either that way, or they mention endo or exothermic. The other way we find delta G is by calculation. What you do is you plug in the value for delta H that you calculate using one of the 3 methods that we know. Delta S is calculated by products minus reactants and the temperature. Plug in all that stuff, you're able to get delta G. If you look, here's an example. They give you the delta H values. Notice the elements are 0. Again, products minus reactants. So here's products, reactants are here. Delta S, everybody has a value, but remember it's in joules. So then we come back over here. We do our delta H, products minus reactants, using the coefficients. You should end up with a negative 92 value. Do delta S. When you do it, products again minus reactants using coefficients, you end up with negative 198.9. Keep in mind that is in joules. Therefore, when you get to going home to supper, you have to change this to kilojoules. So we change to kilojoules. Then we pop out our answer. Our value for delta G is negative. It's negative 32 kilojoules. Therefore, we say the reaction is non-spontaneous, or no, sorry, spontaneous, since it's a negative value. You can calculate delta G values from a table, but they very rarely do that on the exam. Last thing is, remember there's a relationship, a mathematical relationship between delta G and KEQ that we learned in chapter 14. The R that we use is negative, is 8.31. This equation is found in your AP booklet. If they ask you, hey, solve for delta G, the next step they ask you to solve for KEQ, you would just plug in your delta G value. R is a constant. The temperature is going to be at 298 or whatever temperature. Make sure it's in Kelvin. Do your calculations, and then you can solve for K. The other thing you're supposed to understand is the relationship between the equilibrium constant and G. If G is 0, we say the reaction K is equal to 1. That means the reaction is at equilibrium. The other two values are whether or not delta G is negative or positive. If delta G is negative, we say that K is greater than 1. If we say that delta G is positive, we say K has to be less than 1. So we really can interpret the signs for delta G right here. It gives us the idea of what's going on with K. And that is a review of thermodynamics. Key things to remember with thermodynamics are basically this. We need to find delta H, delta S. When we look at it, the key is delta G is equal to basically going home to supper. We have 3 ways to find delta H. By using bond energies, we just went over that, bonds broken, bonds formed. We also can do it by using Hess's law. That's where you flip and cancel the equations. The last way is heat of formation using a table. Delta S, you only can do products minus reactants. To do that, that's the same as the HF down here, heat of formation. So using a table method, you can find delta H that way, or excuse me, delta S that way. And we either do it by calculating delta G, or you can do it, and there's a lot of multiple choice questions on the practice test tonight, the Kung Fu test, doing it by inspection. Looking at the sign for delta H, sign for delta S, and mathematically you can kind of infer or use the table and figure out what it is. And that is the end. Hope you guys have a good night. Knock out the quiz, and I will see you tomorrow. Real talk.